Hello guys, it's great to have you up to this set of slides, of course, and until this class. I hope you are capable of understanding lots of the details involving learning, machine learning in general. Of course, supervised learning in specific. And now we are going to discuss a little more on the spaces that kernels, that support vector machine kernels are built up on. So to start with, we have, of course, mathematically, we have several spaces from the more generic ones to the more specific ones. So a topological space is, of course, more generical. Afterwards, we've got the Hausdorff space, normal space, metric space, normed space, and the inner product space. Actually, when we talk about support vector machines, we are going to work on this kind of spaces, the inner product spaces. So to start, topological spaces require just a set of points, just a set, and their neighborhoods. So we have to have their neighborhoods to understand how one element relate to another one. So there's no need of representing elements in terms of points in a typical Cartesian plane, but instead just elements in a set. Okay. In that particular, of course, in this particular topological spaces, we find like some typical applications, such as web pages connecting to each other through hyperlinks. That's quite typical from topological spaces. Hausdorff spaces, consider we've got like some sort of separation in between two elements. So we've got an element X and an element Y, and there is like a given neighborhood, and given those neighborhoods, if we build up those open balls around, there is still some distance or difference between them. Okay, so this is also called separated space, or T2 space if you prefer, in which points in X have disjoint neighborhoods. That's what we have in Hausdorff spaces, okay? There is a reference, a basic, of course, reference for Hausdorff spaces. Afterwards, we've got the normal spaces. So every two disjoint closed sets, so we've got like some sort of closed set here and here around a given element, X and Y. And those two closed sets have disjoint open neighborhoods. So we can come up with open neighborhoods around each of those closed sets, and there is still some relevant distance in between them, okay? Afterwards, we've got the metric space. Every time we talk about a metric space, we've got a set of points X and a distance metric D, as you can see here, which is a function. That function must satisfy some conditions, okay? First of all, it is defined, of course, if you consider the Cartesian product of X by X, this is the distance, of course, in between every pair of elements we've got in X that is mapped into the real line that's necessary. There are like some additional constraints. The distance in between X and Y must be greater or equal to 0. That means it is non-negative, okay? Or if you prefer, semi-positive. That's the same. And the distance for X and Y, when X and Y are the same element, okay, or they are indiscernibles, that distance is equal to 0. Of course, the distance from X to Y and from Y to X has to be symmetrical. So it has to be the same. And the distance from X to Z happens to be smaller than or equal to the distance from X to Y and plus the distance from Y to Z. That's the triangle inequality. That allows us just compare, for example, x to y, and if we've got like a previous result on y to z, we've got a good, of course, it's so good because we can compare as a result x to z. And afterwards, we've got the normed space. The normed space has a set of points x and some form of computing the vector length. What is a norm? Like the L2 norm, the Euclidean norm, okay? Or some L star norm, it doesn't matter. Any kind of norm you wish to compute. And afterwards, we've got the inner product space. It has an additional constraint. So all those constraints happen here. Of course, in the normed space, it's got all the previous constraints. The metric space has all the other previous constraints. Normal space, the other previous constraints, and so on. So the more general space is, of course, the topological space. And the inner product space has also another constraint, which is we have to have an inner product defined. So we have to have a way of computing inner products, okay? It's quite interesting to mention some examples of spaces. So a complete metric space is inside this metric space. A Banach space is inside the normed space, and the Hilbert space is an inner product space. Okay, that's why we talk a lot about Hilbert spaces, because actually to use the support vector machine we need a inner product space. So the most typical space to be used is a Hilbert space, which allows the computation of inner products. Okay. From that, so I'm going to repeat something here just to make sure I said it all. So of course, in the Hilbert space, a distance metric is defined, the vector norm is also defined, and the inner product is also defined. So it supports the projection of vectors into spaces. And as consequence, it also supports geometry. It supports us to compute geometrical shapes and distances and relations. That's really interesting to think about and to maybe try to imagine what would happen if we couldn't compute inner products. Could we have the solution for the support vector machines? You're gonna check it out. That would be impossible. So by supporting the inner product, we can proceed with projections. And as we did with our first classification algorithm based on geometrical features, I think you guys remember that first algorithm, we can compute the inner products so we can verify how similar a vector is to another one. And of course, we can make projections to build up the separating hyperplanes. So that's why we need to have the support for inner products. Otherwise, it would be impossible to draw those hyperplanes. It would be impossible. So back to the support vector machine optimization. We're going to see the primal and the dual problems here. There is something really essential here. Those two terms. Those two terms are the most important. Here I have a minimization of a positive something, and here a maximization of a negative something. What is this something? We're going to discuss on that now. You know what? We expect the minimization to behave like a convex function as I show here, okay? And the maximization as a concave function. So what I expect actually is that this Q matrix is a positive semi-definite matrix. We're going to discuss on that now. Okay, so that is the point at this in this class, in this particular class. So how can I get how could I guarantee that? So the way of guaranteeing involves like some algebraic analysis. So before going into that, let's remember how we computed Q. Q for the polynomial kernel was computed like this: y transposed element-wise multiplication by some coefficient to ensure to build up a homogeneous or non-homogeneous kernel, x transposed, and then we have the polynomial order here. So of course y represents the vector of classes, x corresponds to the data matrix we have for our training examples, c is a coefficient to build either a homogeneous or a non-homogeneous or inhomogeneous, if you prefer, kernel. And order is the polynomial order of our kernel. So in fact, we expect Q to be a positive semi-definite matrix. What is that? That means every time I multiply some vector alpha transposed by Q by alpha, it has to produce some result greater than or equal to 0. Assume this matrix as an example, the identity matrix. What happens if I compute any kind of alpha before and after, as shown here? Of course, alpha will be a vector belonging to a bidimensional space. So in that scenario, I will have something like this. This vector having alpha 1, alpha 2, and alpha 1, alpha 2. Of course, here it is transposed. Okay. When I solve that, I multiply this by this vector by this matrix, and the result is here. And then I multiply this by the vector itself. I will have alpha 1 to the square, alpha 2 to the square. That will produce a convex function, as you can notice. So what I must ensure is that my Q matrix is positive semi-definite. That will guarantee my support vector machine will find a minimum for my primal problem, for my my minimization problem. That's the primal thing. Yeah, for my primal problem, for my minimization problem. Okay. So what happens, of course, if I consider the dual problem, which just brings like a minus sign in front of all this. This is going to be negative and this is going to be negative, so we're going to have a concave function, just a mirror of this function. Okay. So of course we can find the minimum in this situation. So what happens if instead of having a positive semi-definite matrix, I have this? This is not a positive semi-definite matrix. Let's see what happens. If I have this matrix and I compute the same, my vector multiplied by matrix multiplied by my vector again, I will have this as a result, a negative alpha 1 to the square, positive alpha 2 to the square. This will become a saddle. How could I optimize either a maxima or a minimum in this situation? It would be impossible, just impossible to find the support vector machine solution. So I cannot work with matrices that are not positive semi-definite. Of course, it has become a saddle, as I mentioned. Can we find a minimum or maximum? No, impossible. No, we cannot. So is this applicable to the SVM optimization problem? No way. Okay. So how can I understand if I have a positive semi-definite matrix in my hands or not? Okay. How can I understand what is the difference comparing those two matrices? Okay. Every S support vector machine kernel must guarantee that I have this kind of matrix. Okay. this kind of positive semi-definite matrix. If I have something like this, I will never have a solution for my problem. What happens when a kernel does not guarantee that? What happens is no convergence. What happens is your attempt to converge to a solution is not going to happen. You will not have the solution for your minimization nor for your maximization problems. Okay, but what happens when we have a more complex matrix Q? What happens if I have a matrix like this? How could I confirm if this is a positive semi-definite matrix? I could compute its eigenvalues. So when I compute the eigenvalues, you probably remember that negative eigenvalues will reflect like mirrors in terms of the axis, of the space axis, and that is the result of a known positive semi-definite matrix. So that's the result of a linear transformation resultant from a non-positive semi-definite matrix. So I need to compute the eigenvalues. If I compute the eigenvalues and no eigenvalue is negative, so there is no reflection in terms of my linear transformation. So my matrix is positive semi-definite. So my matrix is positive semi-definite. So I can use it. So my point is, if you've got a matrix like this, let's try here. Let's generate a matrix using like uniform numbers from -1 to +1. I will produce 9 numbers and organize this in a squared matrix 3 by 3. That's going to be my Q matrix. Take a look. What happens when I compute eigen for my matrix? Take a look. One of my eigenvalues is negative. Is this a positive semi-definite matrix? No, it's not. Just to show you, just for the purpose of illustration. So this is what happens in this particular example that I showed you here, okay? So, okay, it's not. So, could I use this Q matrix? No, I couldn't, because one of its eigenvalues is negative. I'm gonna try a different example now with you guys. I just prepared some R code here. I'm going to explain to you. It's quite a simple code. Let me see what is wrong. Oh, okay, here it should be X instead of data. No problem. I'm going to correct that, and you correct in your home. So I'm gonna have X here, and I will have, of course, some additional examples in X over here. That's good. Then we are going to build up our vector Y. This would be much better with -1s here, but it's okay, doesn't matter. Then I will compute my Q matrix as before, as we did before, okay? How can I be sure that my eigenvalues are positive or negative? I can compute the eigen of this matrix and observe the values. Take a look. So many values, so I could plot those values. You might notice that we've got actually eigenvalues very close to 0. So some of those are are high, and the others are like small values. But those small values close to 0 are somehow negative. So you know what? That's not a big problem, because when we compute the eigenvalues, if we have like some eigenvalues very close to 0, that will make no difference in our optimization. But if one of those values is really negative, has a relevant magnitude, that will be a problem. That will be an issue for our optimization. Why that happens? Those particular negative values very close to 0 happen just because we've got some numerical error when we compute the eigenfunction. So there is a numerical error. Okay? So it is interesting to observe this. Very interesting. So some of them may be slightly negative to the precision error due to the computation of our eigenfunction. Can you confirm if this is a positive semi-definite matrix using any other method rather than the eigenvalues? Yes, we can. There is a very, very important method for that, which is the Cholesky decomposition. The Cholesky decomposition decomposes a matrix A into L and L transposed. So actually, this matrix A has to be symmetrical to perform the decomposition. Now I'm going to decompose my matrix Q. So I'm going to do the same here. Let's decompose it like this. Cholesky decomposition of matrix Q. If I perform the decomposition, you're going to observe something. Take a look. It does not work in this case. Why? Because there are some small perturbations in our data that produce or may produce very small but negative eigenvalues, as I mentioned to you. What can I do? What could I do to work this around? There is a solution. In fact, the Cholesky decomposition ensures positive definite matrices. That means my alpha transposed Q, alpha is greater than 0, and not greater or equal to 0, but greater than 0. So that's what Cholesky decomposition requires to perform such a decomposition. But how could I solve this in for practical purposes, of course? Is it possible? Yeah, it is. There is a hint. We can take this positive definite matrix is always diagonally dominant. That means that every positive semi-definite matrix should have in its diagonal. So if I consider matrix Q here, how many dimensions? Let's see, 1000 by 1000. If I take, for example, my diagonal in the position 5 by 5, that's 0. Take a look. What should be the result? Actually, this value, this element should be at least equal to the sum of its row. At least equal to the sum. But actually, it has to be a little bit greater than the sum. So I need to sum up a very, very small value to ensure what is called the Gershgorin circle theorem. The Gershgorin circle theorem tells me that if I have a matrix that is not positive semi-definite, if I sum up a very small epsilon that is greater than the sum of its row into the diagonal, what will happen is that I will obtain a positive definite matrix. How could I perform that? Let's see. What I'm going to do now is I will compute my matrix Q as before. I will have a new Q, as you can see here. Let's take this. I have new Q here. Okay. And then I will sum up a quite small value epsilon equals to 10 to minus 10, and those values composing my diagonal. Take a look. Summing up. Then I will now compute my Cholesky decomposition for this new Q. Take a look, and now it computes. Why it computes? Because if the diagonal is dominant, it has a magnitude, a positive magnitude greater than the sum of its row. It will be diagonally dominant, and consequently it will be positive definite. Now I can do something that is really, really interesting. I can compute how different my new matrix Q after being decomposed, and of course I can solve the Cholesky decomposition, which is Cholesky transposed multiplied by Cholesky. This will provide me the new matrix, as you might think. And here I'm just computing the overall differences in terms of every cell, every element of my matrix, and computing the Frobenius norm, what is called the Frobenius norm, which is a way of computing differences or divergences. Take a look at the total divergence. It is almost nothing. So what I did here was, besides we have some small negative perturbations in the eigenvalues, if I sum up a quite small value in my diagonal, I can ensure that I will have a positive semi-definite matrix after analyzing it using the Cholesky decomposition. And that's so way interesting. Another point, this is the same as mu q. So to prove or to show that this is the same as mu q, I could compute its difference to mu q in terms of the Frobenius norm. Take a look, also a numerical 0, of course, okay? If you are not comfortable in summing up 10 to minus 10, you can come up with a smaller value, a smaller epsilon. Could be like 10 to minus 20, for example. Let's see what happens. Can I compute my Cholesky decomposition? Oh, I couldn't, because one of those values, okay, the row and column 504 has a value that should be slightly greater. Let's try maybe 1 to minus 10 to minus 15. And computing the Cholesky decomposition, no. It has to be greater than that. Let's try to minus 12. And let's compute. No, it should be greater because the element in row 640 and column 640 is still smaller than the sum of its row. Now I could sum up 10 to minus 11. Let's see the result. Oh yeah, that was enough. Of course, if now I compute this difference, what is going to be the difference? It's going to be even smaller because now it is closer to my matrix Q. Here it was minus 18, now 10 to minus 19. What is the difference in between my new Q and its decomposition? It is still minus 24, 10 to minus 24. So it's really, really small. That's really interesting for people that love algebra like myself. I know some of you might think, oh, that's maybe over complex or don't like it, but it's so beautiful. It's so beautiful. What happens if you use the original matrix Q instead? Nothing will work. It's going to work, actually. It's going to work properly. Why? Because those eigenvalues for my original matrix Q are quite close to 0. And that will not affect my optimization. But if they are, as I mentioned before, negative with a relevant magnitude, I mean, they are not close to 0, we are going to have serious consequences. Our optimization is not going to work. We're going to have a result that's not meaningful. So in order to have a meaningful result, you should compute the eigenvalues of matrix Q and analyze them to see if they are very close to 0, if they are somehow negative, or if they somehow they have a great negative magnitude. Okay, just as observation, notice Q is symmetrical. That's good because there are guarantees that eigenvalues will be real. If you guys remember that from algebra, every time we have a symmetrical matrix, eigenvalues will be real. Eigenvalues will be real. Otherwise, they could be complex. Okay, in a complex space. But what happens when the total divergence after computing the Cholesky decomposition gets greater? I mean, What happens if I compute this divergence and it is really, really great? Let's suppose it's going to be like 1 or 2 or 3 or 4 or 10 or 1000. That basically means that the problem I would be solving after summing up something and the diagonal of Q would be a different problem, would be an approximation of my original space represented by matrix Q. So if matrix Q has somehow some negative eigenvalues and I have to sum up in that diagonal a relevant epsilon, or let's suppose an epsilon whose value is like 1, 2, or 5, or 10, or 1000, I will solve a complete different problem. You know, that's a problem, you know, because I will not be approximating my original problem. I will be solving a complete different problem instead. Okay, that's otherwise interesting to assess, to analyze. Okay, so there are adaptations in the Cholesky decomposition. There are some implementations for the Cholesky decomposition in which the code sums up the least possible value in those diagonal cells. That's so interesting. You can search that in R, in Python, in doesn't matter MATLAB, doesn't matter the language or the package you use. You're gonna find some implementations of the Cholesky decomposition that are going to sum up a very small value in the diagonal to make it diagonal dominant. So the value is not going to be the same for every element in the diagonal, but actually it's going to be a different value. It's the smallest as possible value in each cell, for each cell, to ensure the Cholesky decomposition works. And that's so interesting. That's so interesting. And by the way, the Cholesky decomposition only works for symmetric matrices. Otherwise, it doesn't work. In our case, it is symmetric, so it doesn't matter. There is a plus. This type of matrix is also called a Gram matrix. What is a Gram matrix? Gramian matrix. A Gramian matrix is a positive semi-definite matrix. It is a matrix that is symmetric and positive semi-definite. And there is a property here, guys, that is so important. That is so important. As long as the SVM kernel produces a Gram matrix, we can solve the SVM optimization problem. That's nice because, of course, this matrix will be positive semi-definite. Observe something very important. In fact, we do not need to know anything about the kernel itself. So we don't need to know if people use like complex functions to come up with a kernel. If people use like something impossible to analyze or very difficult to understand, it doesn't matter. As far as at the end we've got a Gramian matrix, we can apply it. That means we can just use that Q matrix and assess its eigenvalues or use the Cholesky decomposition to ensure it is going to be positive positive definite. In that case, of course, for Cholesky decomposition, you're gonna solve your problem. That's amazing. You can use SVM. So it doesn't matter if people use like so many packages and complexities to come up with a kernel. That's just so nice. Therefore, we have guarantees that you find the solution for the support vector machine optimization problem. So if you don't have a Gramian matrix, you not have the guarantees for support vector machine solutions. You're gonna get some solution that's not going to be good. I can tell you, it's going to be like just a poor result. So the so-called some people talk about the kernel trick. What is the kernel trick? The kernel trick is actually something, a very important concept, which at the end, which ensures that as far as we obtain a Gram matrix, we have the solution for our support vector machine. So it doesn't matter if your kernel is going to be built upon very complex scenarios or using some different features or whatever. At the end, if I analyze your Q matrix and that matrix is positive semi-definite, what means it is a Gram matrix, what means all its eigenvalues are positive, or if negative, very close to zero, very close, of course, because that's like a numerical zero, I can employ that kernel, the result of that kernel, that matrix, to solve my support vector machine problem. That is what we call the kernel trick. Why kernel trick? Because it doesn't matter how you solved how you analyzed the similarities in between every pair of points you have in your space, in your input space. That's so important, guys. Please look for that term, kernel trick, in the references of this course, please. So how we can verify if a kernel has produced a Gram matrix? That's kind of easy. First of all, the matrix has to be symmetrical. If it's not, you know you've got a problem. Second, it has to be positive semi-definite. What means eigenvalues must be positive. If they are somehow negative, they cannot have a relevant magnitude. They should be very close to zero if they are negative. Actually, we can assess how close to zero they are if we sum up some epsilon in the diagonal and assess that using the Cholesky decomposition. And the Cholesky decomposition helps us a lot to understand how close we are to that ideal matrix, okay, in which all eigenvalues should be positive. There is another point. Of course, you can perform the decomposition like this. Take a look. We could come up with eigen of matrix Q and get the results. Of course, we are gonna see the eigenvalues. What could we do? Which are the eigenvalues smaller than zero? Which are the eigenvalues smaller than zero? We could just take those eigenvalues and make those equal to zero. Okay? Oh, sorry. Here is $. Okay? And of course, now we can do something like this. We can take the eigenvectors multiplied by the diagonal matrix of its eigenvalues, and then product by the transposition of my vectors. And if you remember, we've got a previous class on that. This is going to be a new cube. This is going to be a new cube. What happens if I decompose this new cube and compute its eigenvalues? Let's see. Remember, they are still close to zero, as I mentioned, still negative and close to zero, because that's a numerical error, as I mentioned, guys. So, besides that, you can notice that my eigenvalue decomposition is going to somehow make some of those eigenvalues negative but close to zero because of the numerical errors involved in such a eigenvalue decomposition. So, of course, that's not a big deal, that's not a big problem because they are very close to zero. Okay? But it's important to show. There is something, guys. There is something. Every covariance matrix is a Gram matrix. This is the most important property we've seen throughout the whole course. This means if I get X and I multiply by X transposed, this is a covariance matrix. And every covariance matrix is a Gram matrix. If it's a Gram matrix, of course, if I multiply two Gram matrices, which is Y by Y transposed, we've got another covariance matrix. So the multiplication term by term of two covariance matrices is going to be a covariance matrix, so we are going to have a Gram matrix. That's why, guys, we use all along this course the dot product between every pair of examples belonging to my input space X. That's why, guys. That's why. That's so important, guys. That's the most important piece of algebra we used along this course. I'm going to repeat. Why we have used the dot product in between every pair of examples belonging to my input space X, because that will produce a covariance matrix which is positive semi-definite, which is a Gram matrix. It is symmetric, positive semi-definite, therefore it is a Gram matrix. Therefore, I can use it in my optimization problem. Let me go back here. I can use in those optimization problems to ensure that every time I will have here a convex function. So if it's a convex function, I will find a minimum. And here, every time it will be a concave function because it has a negative value here. So I can find the maximum. That is the most important piece of algebra we used throughout this course. This is so important, guys. Please make sure you understand this. If you didn't, ask me. Just come to the office hours or send a question, whatever. But you have to understand that. That is central. That is the most important result. I'm going to give just another point. So if you create a covariance matrix like X, X transposed, and every time it's going to be symmetrical, and every time its eigenvalues are going to be positive or equal to 0. Of course, if we assess that using the eigenvalue decomposition, you're going to get some values as negative. That happens because of the numerical errors due to the decomposition. What happens if I use that kind of matrix, a covariance matrix, in my support vector machine problem? It's going to work. It's going to work because at the end of the day, it is a Gram matrix. Just as a piece of additional information, if you are interested in carry on understanding what happens in spaces with an infinite number of dimensions. So instead of having a matrix X multiplied by X transposed, producing some Q matrix which has like 1,000 rows by 1,000 columns, or 5,000 rows by 5,000 columns. Let's suppose you have an infinite number of columns and an infinite number of rows. What happens in that scenario? The Mercer's theorem answers that, and the Rees theorem as well. So look for the Mercer's theorem to understand what happens in an infinite dimensional space. That is interesting. That's like a piece of additional information that you might be interested, especially if you come from mathematics, I suppose. Guys, great to talk to you. This was like a movie for me. I mean, this class just unfolds it all, just opens up all the algebraic decisions we took along this course. That's why we used dot products to obtain Gram matrices. And dot products measure similarities, but not just because they measure similarities of vectors in a Hilbert space, which is a linear product space, but also, and most especially because I can use the kernel trick. I can use any kind of matrix Q, again, any kind of matrix Q that is positive and semi-definite is going to provide an amazing and good solution, of course, for my support vector machine primal and dual problems. Oh, going back, primal and dual problems. Guys, great to talk to you. See you in the next video. Bye bye.